So the speaker for today is Dr. Benedetta Vulcani. So without saying anything accurate, so I will let her introduce herself and go ahead with the presentation. So one more thing, I just wanted to ask, so Benedetta, do you mind people interrupting you with questions, or you prefer questions at the end?
It's the same, but the thing is, I'm not sure I will see the chat while speaking, so you can interrupt me. Feel free to interrupt me.
Okay, so I think you can start, or people can also just type questions in the chat and you can read them at the end.
Okay, as you prefer.
Okay.
Okay, so good afternoon, everybody. Thank you very much for inviting me to give this talk. I'm Benedetta Vulcani, and I'm a staff member at the National Italian Institute for Astronomy, that is INAF, and I'm based at the Observatory of Padua. So today, I would like to present you some of the recent results of a survey that is called GASP, which stands for gas stripping phenomena in galaxies. And the goal of this survey is really to understand how galaxies change their properties when there is some mechanisms that try to remove or accrete gas from to galaxies. And as we know that the gas is the fuel for star formation, when we remove the gas, we expect that the galaxy will be quenched. So overall, we want to try to understand how different mechanisms that remove the gas behave in different environments. So let's start with a step back. So we know the galaxies do not look all the same in the universe. We can consider different parameters, and we see that galaxies can span a wide range of properties. For example, in this picture, we see that galaxies can come with many different shapes. So galaxies have different morphologies. On one side, we have the elliptical galaxies that are made of an old stellar population. They are spherical. They form stars at a very low level, or even they are passive, and they have red colors. On the other hand, we have other galaxies that actually instead show a very well-defined spiral structure. They are young, they are star-forming, and they have very blue colors. And these are the late type, the spiral galaxies. In between, we can have the S0 galaxies that are in between the two populations, in the sense that they have a bulge and a disk, but they don't have such a well-structured spiral arm configuration. And then we have also some galaxies that are irregular, that really don't follow any clear pattern. So our goal is really try to understand how galaxies transform and why they come with these different shapes. One thing that we know is that galaxies change over time. If we look at galaxies at very high redshift, they were much more clumpy. They were forming stars at a very high rate. They were typically very dusty, and they were smaller. As time goes by, galaxies become bigger. They form stars overall at a lower rate, and their light distribution is typically smoother. So galaxy transformation happens as a function of cosmic time. And indeed, there are many studies that show that there is a redshift evolution. One of the first studies is the so-called Bachelor-Heromeler effect that shows if we take the fraction of blue galaxies at high redshift and at low redshift, we see that at high redshift, there were many more blue galaxies than in the local universe, suggesting that there is a transformation from blue to red. Similarly, we can look at morphology, and we see that the fraction of S0 galaxies increase as we go from high to low redshift. And this is balanced by the treatment of spiral and irregular galaxies as we go from the high to low redshift. And this suggests that there must be a transformation so that spiral galaxies tend to transform into S0 galaxies from high to low redshift. Then we have also a variation in star formation rate. In the bottom panel here, you see the star formation rate mass relation of galaxies at different epochs. Toward the right, there is the higher redshift. Toward the left is the lower redshift. And what we see that at any given stellar mass, we have a decrease in star formation. Overall, at any given stellar mass, galaxies are forming stars at lower level as we go from high to low redshift. This is even better summarized in the top panel, where we have the evolution of the cosmic star formation rate density, meaning how much all the universe, at the level, all the universe were forming stars. And we see that at around Redshift 2, there is a peak in star formation rate density. And now we are in a phase of decline, meaning that overall, the entire universe is forming stars at a lower level today with respect to the past. So galaxies change their properties depending on time, but this is not the only parameters that affect their evolution. Indeed, galaxies are not distributed randomly in the universe. We have galaxies that are in isolation, they don't have any neighbors, and so they probably live their life, let's say, undisturbed. Then we have some galaxies that are in binary systems, in small groups, up to galaxies that are found in clusters, which are the most massive structures in the universe. Clusters are made of stars and also of hot gas. And so we expect that there is an interaction between this gas permeating the clusters and the galaxies. So we have to expect that also the environment affects the galaxy properties. And indeed, there are many studies that show that the environment plays a role. First of all, one of the first studies is the so-called morphology density relation. Here we have on the x-axis the density of the given environment, meaning that you count how many galaxies there are around each galaxy in a given area. And so we have denser regions where there are more galaxies and less dense regions where we have less galaxies. And what it has been found that overall elliptical galaxies are preferentially found at higher densities, while late-type galaxies are preferentially found at low density. So this suggests that when we have a lot of galaxies in the same areas, the galaxies are not able to maintain their shape and their morphologies, they lose the spiral arms, and so it's easier to find galaxies with an elliptical shape. Then we can also look at the color. Here on the y-axis, we have the local density again, and on the x-axis, we have the stellar mass. If you just fix a stellar mass, what you see is that the galaxies at higher densities are preferentially red, while galaxies at lower densities are preferentially blue. So yet again, the environment affects the properties of the galaxies. However, this plot also shows that the situation is complicated by the different stellar mass. Now, if you fix a given overdensity and you look at trends as a function of stellar mass, you see that least massive galaxies are blue, while most massive galaxies are typically red. And so this warns us that we also have to keep into account the mass of the galaxies when we try to understand the role of the environment. Finally, we can also look at the star forming properties, and here we see in black the cluster points, in green the field galaxies, and we have again the star formation rate mass relation. While cluster galaxies can be as star forming as galaxies in the field, there is a population of cluster galaxies with reduced star formation rate that stay well below the typical relation, suggesting that there must be something that suppresses the star formation in a cluster. I keep saying that there is something that suppresses or that the environment can alter the properties of the galaxies, but what does this actually mean? The fact is that in each different environment, we can have a different set of physical mechanisms that can affect either the gas component of the galaxies or both the gas component and the stellar component. And these mechanisms are really environmental specific mechanisms, in the sense that some of them take place only in less dense regions, some others take place only in very massive systems. Just to say an example, in the field, we can have mergers or interaction, galaxies that cross each other quite slowly, they can have some gravitational interaction. On the other hand, when we have a massive clusters, there is a lot of gas within the cluster, and so there is an interaction between the galaxy that enters a cluster, for example, for the first time, and this gas. And so the gas of the galaxies can be removed. And these are called hydrodynamical processes, because these processes affect only the gas component, leaving the stellar component unaltered. So each of these different mechanisms take place in different environments and also are expected to leave a different patterns on the gas and on the star distribution of the galaxies. So one of the goals of my research is try to understand the effect of the environment on the spatially resolved properties of the galaxies. Indeed, in all the plots that I've shown you so far, each point represented a single galaxy. Instead, we know the galaxies are made of different components. We have a bulge, we can have some spiral arms, we have some regions that are more star forming, some regions that are less star forming. So sometimes just using one single value to represent the full galaxy might not be as representative as we would like. But this is what was done until a few decades ago. Typically, people would study galaxies using a fiber spectroscopy or a slit spectroscopy, meaning that they would observe the full galaxies just with one observation and would take the average value obtained within that fiber to describe the full galaxies. Then, if you are lucky enough, you can get the full galaxy within this fiber. But if the galaxy is very big or the fiber is very small, you can just observe the core of the galaxy. There is a question in the chat. Can you please read me the question? Because if I can see my mouse to move it.
Yes. So the question is
okay, yeah, so I didn't catch.
No, I can't hear you, I'm sorry.
Okay, I'm saying I didn't catch.
No, I can't hear.
Okay, so let me read the question. So he's saying he didn't catch the difference between evaporation and RPS.
Okay. I'll explain later run pressure stripping, typical and the other processes. But with evaporation, you just let me go back. Let's see if I can go back here. So the thermal evaporation actually removes the gas in the similar way at all position of the position of the galaxies. Instead, run pressure stripping is really part of the gas is displaced and stripped and will leave a tail behind. I will show, most of the talks is based on run pressure stripping, so we'll come back later on this. So I was saying that, yeah, typically when you have just the fiber of the slit spectroscopy, you obtain just a biased information of the galaxy, and then from the portion of light that you have, you just infer the global value. And so the results might be biased. In the last decades, a number of different techniques have been developed to actually study the galaxy separately in each position. And this is the so-called spatially resolved data technique. And so we can have the IFU data. This means that for each position of the galaxy, we can have access to a spectrum. One of the most famous instruments is MUSE on the VLT. So we really can have either one spectrum at each position of the galaxy, or we can extract an image of a galaxy in a given at a given wavelength. So this is very powerful to contrast different portions of the same galaxy and see whether something is affecting only, for example, the stellar component and not the gas component, or vice versa, or if different portions of the galaxies really feel different environment. Motivated by the interest of understanding what are the physical processes that affect the gas component in galaxy, and thanks to the advent of these IFU techniques, we studied the gas stripping phenomena in galaxies, which is a program that is really interested in understanding where, why, and how the gas is removed. We want to quantify if the gas is removed, by how much gas is removed, which is the most probable physical process, what are the consequences of these gas removals on the galaxy life, what are the properties of the galaxies even before the gas removals, how these gas removals can be connected with other parameters, such as the central black hole within the galaxy, and what is the role of the environment. GASP is led by Bianca Poggianti here in Padova, but it's really an international collaboration. And you can see highlighted the people that have been contributing the most to the project. The backbone of GASP is a large program on MUSE. We got 120 hours with MUSE. MUSE is a great instrument because it's characterized on a very large field of view, 1 by 1 arc minutes. It has a very high sensitivity, a good spatial and spectral resolution, and it covers all the optical wavelength, and it has a quite a large wavelength range, so we can really access to a large number of galaxies. And we observe for each galaxies, we get up to 100,000 spectra. So we can really have information not only in the galaxy core, but also in the outskirts. Quite soon, though, we realized that to really understand all the gas removal processes, just the optical view is not enough. We really need to have a multi-wavelength approach to really characterize all the gas phases. So in addition to the optical data with MUSE and also with some extra data with extruder, we have started collecting some additional information, especially for the galaxies that look more promising and interesting. So our sample now range from the sub-millimeter data with apex, ALMA, and so on. We have H1 data, UV, X-ray, radio, and so on. So we are really trying to build a multi-wavelength overview of the galaxies. But today, I will just focus mainly on the results from MUSE data. So how did we select the galaxies? What we did was first, we visually inspected the B-band image of galaxies that were in clusters and in the field. And we selected those galaxies that show some unilateral debris, some asymmetries in the B-band images that were suggestive of stripping events. We tried to exclude clear case of mergers and interactions because we really wanted to characterize the gas stripping only processes. So we ended up with a sample of about 400 stripped candidates that is published in the Poggianti et al. 2016 paper. Then we selected a subset of these galaxies that are 94 galaxies that were the most interesting and actually that allowed us to map a quite large stellar mass distribution and halo mass distribution. And so we selected 94 stripping candidates. On top of that, we observed 20 other galaxies that had no morphological anomalies, both star-forming and passive, that constitute our control sample. Thanks to the large area coverage of MUSE, we can, at the redshift of interest, that is between redshift 0.04 and 0.07, we can observe a region that is 60 by 60 kiloparsec. And so we can really see very outside the galaxy. We are really sensitive to the outskirts, that it's where the interaction between the environment and the galaxy happens. So we can reach up to 10 effective radii. So with respect to other surveys like MANGA or CALIFA that really can count on a huge number of galaxies, the main features of GASP are the large galaxy area coverage. Many other surveys really focus on the central parts of the galaxies. We cover a wide mass range, and we really are targeting galaxies in different environments. How does the strategy work? So we selected these galaxies. This is just one example of this galaxy. Then we observe it with MUSE, and we have a so-called data cube. So and here at each position of the galaxy, we obtain a spectrum like this. So we have about 100,000 spectra like this. And then we proceed with the analysis. From the analysis of the emission lines, we can obtain information on the line fluxes. This helps us to compute the gas kinematics. We can compute the gas and gas metallicity, the ionization parameters. We can understand which is the main ionization mechanisms. So if there is an AGN, if it's star formation or shocks or what else, we can use the ratio of we can use the Baryon decrement to measure the dust, the presence of dust. We can compute the star formation rates and the ionized gas mass. Then we also analyze the continuum, and from the fitting of the continuum, we can obtain information on the stellar properties. So we study the stellar kinematics. We have a spectrophotometric code that gives us information on the stellar population properties, meaning that it allows us to understand how much star formation rate there was at different epochs of the galaxy. So we can have the star formation rate in 4 different H-beams. We have information on the mass and luminosity weighted ages, so we can understand when the bulk of the mass of the galaxy was formed, when there was a very last burst of star formation, and overall we can compute the total stellar mass. And so this is just an example of an H-alpha map. And so here, each point that you see actually comes from a different spectrum. So we can really have a spatially solved map of all the information that I just listed. This is a collection of one of the most extreme cases of galaxies that shows these tails. These are the RGB images. If we look at the H-alpha images that are a good proxy for star formation, we really see the development of these long tails. And so we want to understand what are these tails. These galaxies are the best cases of candidates of ramp pressure stripping that we call jellyfish galaxies. Jellyfish galaxies are by definition galaxies that really show long tails of materials that is removed out of the galaxies. There are in the literature many examples of this population, but before GASP, everybody was just studying 1 or 2 galaxies at the time. While thanks to GASP, we can really build a big sample that allow us to perform statistical studies. Jellyfish galaxies are the byproduct of ramp pressure stripping. Ramp pressure stripping is a process that happens when a galaxy first enters a cluster environment. So in this video, we have a normal spiral galaxy that is moving and entering the dense intracluster medium. And as you see, it develops these tails. These tails are due to the fact that as the galaxy moves, if the medium is dense enough and hot enough, the galaxy is not able to retain its gas anymore as it moves, and so it leaves behind this trail. So the ramp pressure stripping depends on the velocity of the galaxy and on the density of the medium. And so the goal of GASP is to really understand in ramp pressure strip galaxies the properties of these tails. Ramp pressure stripping has been largely studied in simulations, and there are a number of criteria, let's say, that according to simulation, galaxies must meet to be ramp pressure stripped. So when we have ramp pressure stripping, we expect these long tails of gas, and we also expect that there are new stars that forms in knots in these tails. The ramp pressure stripping typically happens outside in, meaning that the first gas that is stripped is in the external part of the galaxies, and then as the external part is removed, progressively the internal gas it gets removed. So we end up with a truncated disk in ionized gas with respect to the stellar continuum. In this process, the star formation rate can be enhanced according to simulation, but the final stage is really a suppression of star formation rate because ramp pressure stripping will eventually remove all the gas. So we will be left with a passive galaxy. In this process, the gas kinematics is expected to be very disturbed. So now we can see if our galaxies actually do meet all these criteria. Before doing that, I just wanted to highlight that in our strategy, we selected the galaxies in the B-band images. So we are very sensitive to new stars that are formed in the tails. But actually, in observation, it has been shown that we can identify the ramp pressure strip tails through a wide range of different observational setups. And actually, each different selection brings us a slightly different subsample of ramp pressure strip galaxies, because each selection is sensitive particularly to a given population. For example, if we look at the tails in H1, we will be more sensitive to galaxies that are at the initial phase of stripping, because H1 is the less bound gas, and so it's the easiest to be removed. If we look at X-ray or at radio wavelength, actually instead we will see galaxies that are at a later stage, because the emission in radio wavelength, for example, will last longer. And then there are other techniques to select the ramp pressure strip galaxies in UV, in narrowband imaging, and so on. So the first criterion that the galaxy must pass to be a candidate for being ramp-pressure stripping is ramp-pressure stripped is being a member of a cluster or a group. Indeed, we really need a dense intracluster medium that is able to strip the galaxy, the gas of the galaxy. In this plot, you see on the x-axis the position of the galaxies within the cluster, and on the y-axis the ratio between the velocity of the galaxy and the velocity dispersion of the cluster. And ramp-pressure stripped galaxies are expected to be, according to simulation, at very high velocity y-axis and at very close to the cluster center. And in this plot, the green stars are the galaxies that are the best candidates for ramp-pressure stripping. And you really see that they really are located at high velocity or at very positive or very negative velocities and are close to the cluster center. Another thing is that we need to see these long tails. And indeed, many of our galaxies show the presence in H alpha of these long tails. Then we can compare the stellar kinematics and the gas kinematics, and ramp-pressure stripping, being an hydrodynamical process, is expected to affect the gas kinematic but do not affect the stellar kinematics. Here we have an example. On the right, we have the stellar kinematics, and on the left, we have the gas kinematic. And you can clearly see that the stellar component is rotating completely undisturbed, while the gas component on one side, especially on the disks, follows the rotation of the stars. But in the tails, the gas distribution, the kinematics, is disturbed. And the rotation in the tails maintains the rotation of the star in the disks, but they are kind of slower down. Then another criterion is that the tails must be developed in recent times. So here we have 4 star formation rate bins. As I said before, we have spectrophotometric models that tell us the amount of star formation at different epochs. In the bottom rows, we have the old stellar populations. In the upper rows, we have the young stellar population. And you can see that these tails really developed, forming stars only in the recent epochs, about 6 times 10 to the 8 years ago. So it's really coincide to the moment when the galaxy entered the clusters and it starts developing these tails. So once we have confirmed that a subset of our sample is really undergoing ramp-pressure stripping, we can start studying the general properties of these galaxies. And the first question is to understand if there is star formation in these tails that we have characterized. So overall, our galaxies have these long H alpha tails that can be as long as 100 kiloparsec. We check through the BPT diagrams what is the dominant ionization mechanisms, and we see that it's photoionization by young massive stars. So there are really new stars that are born out of the stripped tail. What we see, this is an example of a galaxy, and you really see in the tails the presence of very bright knots. And so most of the star formation really happens in these knots. These knots are very cold. They have a median velocity dispersion of 27 kilometers per second. And so we are really seeing these star-forming clumps that are born in situ. And the luminosity, the H alpha luminosities of these clumps are typical of the giant H2 regions. And these clumps have a typical stellar mass of a few times 10 to the 6 solar masses. If we compare how much star formation there is in the tails, we see that in our galaxies, it can range from few percent up to 20%. So now we can ask ourselves how much this star formation in the tails contribute to the total star formation rate of the galaxies. And so we can compare the star formation rate mass relation of ramp-pressure stripped galaxies with the star formation rate mass relation of the normal undisturbed galaxies. So we compute the star formation rate from H alpha, we have the stellar masses from the photometric model, and then we simply sum the total the star formation rate and the mass that we have in each spaxel to have the integrated values. And here we have in black the galaxies in the control sample, and then color-coded ramp-pressure stripped galaxies of different degrees of stripping. But let's compare the black points to all the rest. And what we see is that at any given stellar mass, there is an enhancement of the star formation rate. And this is true both when we consider the star formation that is both in the disk and in the tails, but also when we just consider the star formation rate in the disk. So the disk of Rampressure strip galaxies have an enhancement in star formation compared to undisturbed galaxies. We know that at the end, the Rampressure stripping will lead to quenching, but there is a phase we are witnessing, a phase in which Rampressure strip galaxies have an enhancement of the star formation. We can now ask, where does this enhancement happen in the disk? Is it just in a particular portion of the disk, or is it throughout the disk? So we can look at the local star formation rate mass relation. And so we see, instead of plotting 1 point per galaxy, we really plot all the spaxel, all the points, the information that we have for all the galaxies in the sample. And so here we have the spatially resolved star formation rate versus a spatially resolved stellar mass. In red and color-coded red, orange, and yellow, are the points for the control sample, and in blue are the points for the stripping sample. And we really see that at all masses, we have at all the spatially resolved masses, we have an enhancement. So even on the kiloparsec scales, stripped galaxies present a systematic enhancement, and this enhancement occurs at all distances from the cluster center, from the galaxy center. It's independent on the degree of stripping and on the inclination of the galaxies. We just see that there is a dependence on the stellar mass because this excess is largest for the less massive galaxies and decreases within the increases mass. So the Rampressure stripping works as a wave that really enhances the star formation throughout the full stellar disk. Another quantity that we can characterize from a statistical point of view, now that we have seen that the Rampressure stripping affects the star formation rate, is the mass metallicity relation. From the emission lines, we can obtain the information on the gas metallicity relation, and we measure the metallicity at the effective radius, that is the characteristic radius of the galaxies. And here we have the mass metallicity relation for the strip galaxies in pink and for the field and cluster undisturbed galaxies in black and gray. And overall, what we see is actually that the two populations really follow the same mass metallicity relation. There is no significant offset. And the dispersion of this relation only slightly depends on the star formation rate of the galaxies, and this is in agreement with the existence of the fundamental mass metallicity relation. We also only see a deviation for the very low mass galaxies, but we still don't understand why this happens. So even though Rampressure stripping is shuffling the gas, what we find is that at the effective radius, the chemical properties of the galaxies are independent on Rampressure stripping. We can now look at the metallicity of the gas that is in the tail. So we select the galaxies with the longest tails, and now we go and measure the metallicity in the clumps that are in the tails that we have seen before. So in the, if you look at on the left panel, in the bottom panel, you see where we highlight a number of different tails for this galaxy. And then on the right panels, we measure the metallicity gradients, meaning the value of the metallicity in each clump as a function of the distance of the clump from the galaxy for each tail separately. And we see that overall, there is a strong negative slope of this gradient. This gradient is very negative, and it's much steeper than the typical gradients that you observe in the disk of the galaxies. So we really want to understand why these gradients are so negative, and they weren't never seen in the literature. So we have three working hypotheses that we can test. On one side, as I said at the beginning, the Rampressure stripping take place outside in. So meaning that the first gas that is stripped is the very external one. And it's also known that in the external region of the galaxies, we have a metallicity that is lower than the metallicity that we have at the center of the galaxy. And so one hypothesis could be that we are seeing in the tail some gas that was stripped very farther out. But if we consider the metallicity gradients of the galaxies, we should really go up to 5 or 6 effective radii, and then this gas should migrate into the tails. But this is very unfeasible because both the simulation and observation show that tails do not narrow with distance. So the gas is really, the stripping proceed orthogonal to the motion of the galaxy. So it's very unlikely that we are seeing gas stripped very far away that ends up in the narrow tails. Another problem could be that the approaches that we use to compute metallicities through the different line ratios, it's not valid anymore in the tails, because in the tails, there could be some shocks and some other processes that could alter the validity of the prescription. But we also tried a more conservative approach, excluding all the galaxies where we have some oxygen 1 excess that it's really indicative of shocks or other processes. And we still see for the clamps that we are really 100% sure that they are powered by star formation, we really see still this decline. So it shouldn't be an issue of the way we computed the metallicity. The final possibility is that we are witnessing a mixing between the intracluster medium and the stripped interstellar medium of the galaxies. And indeed, simulation find that for the clamps that are stripped out of a galaxy, as we move away from the galaxies, the fraction of intercluster medium increases. And so we want to see if this is something that could explain the very steep metallicity gradients. So we assume that the metallicity that we measure in the clamps must be a linear combination between the metallicity of the interstellar medium, that is the metallicity of the galaxy, times the fraction of interstellar medium that we see in that clamp, plus the metallicity of the intercluster medium and the fraction of the intercluster medium. So we assume as the metallicity of the intercluster medium what other works have typically adopted, that is 0.3. Then we assume that the fraction of the ICM plus the fraction of the ICM must be equal to 1. The metallicity of the clamps is the one that we measure. The metallicity of the interstellar medium is the metallicity at the border with the disk. And then we can resolve this simple equation to obtain the fraction of the intercluster medium. And this is the value that you see on the right to right axis of the plots. And you can see that in some cases, the farthest clamp can have more than 50% of mixing between intercluster and interstellar medium. And so this is the first observational result of what simulations have predicted, that is, that we are witnessing a mixing between the two gases. As I said, the ramp ratio stripping leads to quenching. And indeed, in our data, we already have some signs that ramp ratio stripping is really quenching fast the galaxies. In the plot in the center, there is the galaxies that I showed you also before, and you see in gray contours, the contours of the stellar disk. And you see that in the bottom part, there is a stellar disk, but there is no gas anymore. And the spectrum on the left show typical signatures of post-starburst galaxies, suggesting that here the gas has been really stripped very quickly and the star formation has been interrupted very abruptly, as it is in the case for post-starburst galaxies. On the right, there is another example where we have a truncated disk. The gas disk is smaller than the stellar disk. So again, we are seeing that the ramp ratio stripping is removing the gas outside it. And indeed, we also have some galaxies in our sample that really are post-starburst galaxies. Here in these 4 columns, we have again the star formation rate at different epochs for the galaxies, and we really see that, sorry, I missed the label of the ages, but we really see that in the last few 10 to the 8 years, the star formation is fastly quenched. And also the spectra on the left are really spectra typical of post-starburst galaxies. So we confirm that in these galaxies, ramp ratio stripping may create the post-starburst signatures. as I mentioned before, we actually have different observation at different wavelengths, and this is just to show you the richness of our sample. In this galaxy, for this galaxy, for example, we have both H-alpha, the UV data, we have the ALMA data, the X-ray, the radio continuum, the H1, and comparing all of these maps, we can really date the age of the clumps, and we can really try to build a history that gives us information about really how this gas was removed. Until now, I talked only on, of galaxies in clusters. I don't have time to go through all the other mechanisms that we have investigated, but just to show you that we developed a diagram to really understand what is the physical mechanisms that affect the properties of the galaxies in the less dense environment. Combining MUSE information and the knowledge of the environment, we can really classify all of the galaxies in our sample. And so we detected some galaxy-galaxy interaction, merger, ramp pressure stripping also in groups, gas accretion, what we call cosmic web enhancement, because we see the galaxies that are in filament have an enhancement of star formation in the surrounding, and we think that it's due to the passage of the galaxy through the filaments. We see cosmic web stripping, that it's similar to stripping, but for dwarf galaxies that are in isolation. And we also see some galaxies that simply ended up their fuel of star formation, just consuming all the gas that they have. And these are starvation candidates. Now that we have classified each galaxy, we can quantify how good GASP has been in selecting the candidates to observe. So if we consider only the cluster population, we see that 80% of the stripping candidates were indeed confirmed of being undergoing ramp pressure stripping. So the success rate in clusters is very high. In contrast, in the field, we find a very large number of different mechanisms. And so this suggests that the visual selection that it's based on optical images is really not enough to select processes that affect only the gas component and not processes that affect both the stellar and gas component. So to characterize the main mechanisms in the field, we really need the IFU data. Since we know that the success rate of GASP in cluster is very high, we can also just try to give an estimate of how many galaxies in the universe, in the local universe at least, go through a ramp pressure strip phase. So we can try to quantify the incidence of ramp pressure stripping in cluster by comparing the stripping candidates of the Poggianti et al. 2016 catalog that just include all the possible candidates with the undisturbed galaxies that are in clusters. We just take the fraction of the ramp pressure stripping candidates with respect to blue galaxies that are bright, late type, are cluster members, and are within 2 virial radius. And what we find is that 30% of the enfolding cluster population show sign of stripping. And here, just focus on the purple line. Here we see this fraction as a function of some properties such as the observed magnitudes, the stellar mass, the color, the morphological types, and the distance from the center. And what we see is that actually, if we look at very bright objects, almost all of the galaxies show sign of stripping. Also, if we look at very blue objects with B minus V color very close to 0, most of them are really undergoing ramp pressure stripping. So this suggests that the ramp pressure stripping is a very important mechanism. If we make some assumption on the visibility of the tail and of how long a galaxy maintains its blue colors in clusters, we can conclude that almost all galaxies undergo a ramp pressure stripping event that it's visible at optical wavelengths. And this again suggests this, our assumption might be maybe too generous, but in any case, it suggests that the ramp pressure stripping is extremely important, an extremely important process that affects the vast majority of cluster galaxies. Now, just to conclude, just to show that this has been done in the local universe, but we are moving toward higher redshift. We have 10 clusters, again observed with MUSE in a redshift range between 0.3 and 0.5, And we are selecting Rampressure strip candidates and confirming the Rampressure stripping is enacted also on these clusters. And even at higher redshift, MUSE gives us information on a wide range of properties, from emission lines to the stellar and gas kinematics, the ionization mechanisms, the presence of dust. And also we have for the first time access to the O2 lines that in the optical at low redshift, it's outside the MUSE wavelength. And we found for the first time an excess of O2 in the tails of Rampressure strip galaxies. But this is something that we are still investigating. The important thing that already at redshift 0.3, we see that the great majority of the blue cluster members really either are already passive or show tails due to Rampressure stripping. So Rampressure stripping must be a very important process already at higher redshift. So just to conclude, I hope I have convinced you that MUSE provides some exquisite data to understand what are the physical processes that affect the gas content of galaxies. With GASP, we could really characterize the different processes across a wide range of stellar masses and environment. And we were able to identify the physical process for each of our 94 stripping candidates. In clusters, the success rate of GASP is very high, while in the field, there are many different mechanisms that can produce very similar signatures on the B-band images. We have found that in clusters, both in the local universe, but also at high redshift, Rampressure stripping seems to be by far the most common mechanisms. And with this, I can stop here.
Thank you. Do you want to clap for her now? Or? Okay, so let's have a few questions. Maybe I should start. I'm not sure how to ask the question. So it's kind of you had the part where you said you were trying to study how the environment, but you wanted to look at all the points separately. So I'm not sure.
Sorry, can you say it again? I didn't hear.
Yeah, so I said because most of the studies, what they generally do, as you mentioned, is that they use one point for the whole galaxy, but then you had this part where you were trying to look at the points individually. So when you do that, was there like a specific trend at the core of the galaxy that you can see is it more affected compared to the edges of the galaxy?
No,
when you had the metallicity stuff.
No, I'm not sure. Sorry, because my connection is not very well. I'm not sure I really understood. But no, we computed. Yeah, when we have about 100,000 of spectra for each galaxy, but then we can sum up all the pixels, and so we obtain the global values. And so far, we have measured in terms of global values the star formation rate and metallicities. We haven't characterized yet the star formation histories, for example, as global values. We are just looking galaxy by galaxies the trends. Does this answer?
Okay.
I have.
No, sorry, I can't hear.
Can you type your question in the chat? It seems like your mic keeps cutting on and off.
Okay. Let me try one more time. I think it's fine now. In the how
I think you should type because it keeps breaking.
Yeah. Okay.
Can you mute yourself when you're typing?
Okay.
Your keyboard is a little bit loud. Okay, so just had another question. So you had the flow chart with all the possible causes of gas stripping. So for now, like, are we sure the RPM is like the most dominant effect?
Yes.
Okay.
And well, in clusters, it's the most dominant effect, but this was mainly done to characterize galaxies that are not in clusters, but in groups or in the field or in binary systems that are everything that was outside the cluster. And we really see that in some cases, in some groups, we can detect Rampart stripping, also at the group level, suggesting that also at the group level, Rampart stripping is important, but it's not the dominant mechanisms by far as it is in the cluster.
Okay. I'm going to read his question now. So can you generalize how long the compression phase takes and at what radius to the center of the core?
Well, this, it's hard to be done with observations because each galaxy is very different, let's say, and also we suffer quite a lot by inclination, by the different stage of Rampart stripping, also because when you see a tail or not so long tail, let's say, it's very hard to understand if the stripping is at an initial phase or if we are seeing the end, it's in the very final stage. This is something that simulation should answer better, but I think that there are no estimates yet out. But in general, Rampart stripping, on the spatial scale, let's say, Rampart stripping should deprive the gas from the galaxy in less than 1 giga-year, just to have, and so depending on how big the galaxy is, also it will take a different time scale. But we don't have the statistics to really subdivide galaxies in so many categories to find a final conclusion.
And how can we tell just by looking at the test if it's RPS, the dominant mechanism?
Well, the thing is that we started from this, we started by the visual classification. So we look at the B-band images and we selected the galaxies that we thought were dominated by Rampart stripping, by stripping phenomena in general, but especially Rampart stripping for clusters. Then we observed a subsample of those galaxies, and in 80% of the cases in clusters, this was Rampart stripping. So we can assume that if we observed 2 times the same sample, we would obtain, and again, another 80% of Rampart stripped galaxies, because they meet, it's not just that we look at the tails, but they meet all the criteria, that is kinematics is disturbed in the gas, but not in the stars. The tails developed in a recent epochs, they are in clusters, they are moving quite fast within clusters, and so on. And so it's just by statistics. If most of the cases that we selected as good candidates indeed have been confirmed being Rampart stripped, it means that it's a very important mechanism in cluster.
Okay, I don't see any other question in the chat. I think we still have a few more minutes, so if anyone has to ask a question, let him shout now. Okay, so if there's no further question, we're going to thank Benedetta once more, and we're going to proceed to end the session. Thank you very much.
Thanks.
Okay.
Bye-bye.
Bye-bye. Goodbye, guys.